Hi everyone. I will talk about some aspects of Chern-simons matter theory and the implication towards a Bosonic exclusion principle. This talk is based on these two papers, which were done in collaboration with Siraj Minwala, Naveen Prabhakar, and Tarun Sharma. I will start with a brief introduction about these theories, and then I will briefly discuss about some of the results of these theories. In three spacetime dimensions, other than the Maxwell gauge theory and its non-abelian generalizations, namely Yang-Mills theory, there exists a completely different type of gauge theory, and this is known as the Chern-simons gauge theory. And this theory is local, Lorentz invariant, and gauge invariant, which satisfies the usual criteria for the sensible gauge theory. However, pure Chern-simons theory is a topological theory, and it has no local dynamics of the gauge fields. So as far as the local dynamics is concerned, it seems rather trivial, since the equation of motion for the gauge field is given by F mu nu equals 0, the solutions of which are just pure gauges or flat connections. However, there are various ways that Chern-simons theories can be made more interesting and non-trivial. In our case, we focus on the Chern-simons gauge theories coupled to dynamical matter fields in the fundamental representations of the Chern-simons gauge groups. These theories are interesting for many reasons. For example, these theories are exactly solvable in the Largent-Tooth limit, and some of these theories have holographic dual descriptions. And more importantly, these theories exhibit conjectured Bose-Fermi duality. Roughly speaking, there exists a considerable evidence that the fermions coupled to Chern-simons gauge fields is dual to a theory of bosons coupled to level rank dual Chern-simons gauge fields. In other words, these two theories describe the same physics. Okay. So, because we tend to think of bosons and fermions as qualitatively different, the Bose-Fermi duality seems to be counterintuitive. One might ask, how can the Bose-Fermi duality can be reconciled with the difference between the bosonic and fermionic statistics? In particular, how do bosonic and fermionic thermodynamic ensembles manage to exhibit the same physics when coupled to Chern-simons, despite their apparent differences? To understand this, it is useful to focus on an ensemble at finite chemical potential and zero temperature, because in this case, the differences between the Bose and Fermi statistics intuitively appears to be more prominent. Okay, so for free fermions at finite chemical potential, and in the Fermi sea, all the single particle states at energies below the chemical potential are occupied exactly once. And for free bosons, it behaves in a rather singular manner, because they form a Bose condensate, and a finite charge state of free bosons with any possible charge lives at a single value of the chemical potential, which is equal to the mass of the boson, and no other states are occupied at all. Okay. Now I will explain how this picture is modified in the presence of Chern-simons interactions. In matter Chern-simons theories, there is a toothed coupling parameter lambda, and the parameters of the dual fermionic and bosonic theories are related to each other by this expression lambda f equals 1 minus mod lambda b. And free fermions correspond to the end where lambda f equals 0 or lambda b equals 1. And free bosons correspond to the end where lambda b equals 0 or lambda f equals 1. And this allows us to interpolate between the free fermions and the free bosons. Okay. Now we summarize how the behavior of the fermions and bosons are modified at a generic value of this coupling lambda. Okay. In the fermionic descriptions, the Fermi sea behavior is qualitatively unmodified at all values of the coupling. And at every value of the coupling, a Fermi sea can be thought of as a sea of quasi-particles. And properties of these quasi-particles can be computed exactly as a function of the coupling. And as for the free theory, each quasi-particle state below the chemical potential is occupied exactly once. On the other hand, the bosonic state at finite chemical potential turns out to depend qualitatively on the coupling of the theory. In particular, it turns out that each of the states below the chemical potential are occupied with an occupation number 1 minus mod lambda v by lambda b. Okay. Even though the bosonic and fermionic descriptions are both in terms of single particle states with different occupation numbers, these two states have the same overall charge, meaning when you sum over all the colors, the net occupation numbers are equal. In the case for bosons, there are NB colors, and for fermions, there are NF colors. And from the conjectured duality map, it follows that NB times 1 minus mod lambda B by lambda B equals NF. So in summary, the interaction effects resolve the singularity of free bosons in a finite chemical potential and turn the Bose condensate into one that has a dual descriptions in terms of the Fermi sea. Okay. Now, the previous discussion suggests that the Largen bosonic Chern-simons theory appears to obey an exclusion principle. This is because the upper limit of the occupation number in the case of fermions is 1, whereas in the case of bosons, the upper limit on the occupation number of the single particle states is a finite number n, which is 1 minus mod lambda b by mod lambda b, and the second equality follows from the definition of the two coupling. Okay, and unlike the case of fermions, this occupation number is not an integer. But once we sum over all the color indices, the total number of bosons that one can add in a given single particle state is an integer. Similarly, after summing over all possible colors for the fermions, the total number of fermions that one can add in any given single particle state is NF, and it follows from the Bose-Fermi duality map that NF equals KB. Okay, thus it is now easy to see that the Bose exclusion principle is the dual descriptions of the Fermi exclusion principle. We briefly explain this point further and how it fits with the idea of level rank duality. For this, consider M fermions in a given single particle state, which transforms in an SUNF representation with a single column and M rows in the Young diagram. And the fact that M is less than equal to NF is a statement of the Fermi exclusion principle. Now consider a collection of M bosons, each of which occupies the same single particle state, and these M particles transform in the SUNB representation with a single row and M columns. And the Bosonic exclusion principle asserts that the number of boxes in the row cannot exceed KB. Okay. This fits with the idea of level rank duality, because under level rank duality, the representation with a single row, single column and M rows map to a representation with a single row and M columns. Okay. And so the restriction M less than equal to NF is dual to M less than equals KB. So before I finish, I will just briefly outline how the occupation numbers are modified at finite temperature. The average occupation number of each quasi-particle state with energy epsilon and charge q is given by this expression, where rho f is the holonomy distribution functions. In the finite, in the infinite volume limit, this holonomy distribution function takes this tabletop form, and in this case, the above integral can be explicitly performed. Okay? And the expression for this average occupation number in this case is given by this expression, which can be thought of as a finite lambda generalization of the occupation number formula for the Fermi-Dirac statistics. And as expected, in the lambda goes to 0 limit, this modified occupation number reduces to the occupation number of the free fermions. And similarly for the bosons, the average occupation number in the large volume limit is given by this expression. And using the tabletop distribution, one can similarly perform this integration. And the occupation number for the bosons explicitly takes this form. And this can be thought of as finite lambda b generalization of the occupation number formula for the Bose-Einstein statistics. And it so happens that this NF bar for the fermions and NB bar for the bosons, they are not equal to each other. But what happens is that under Bose-Fermi duality, a capital NF times NF bar is equal to the capital NB times NB bar, which is also expected because we see that the total occupation numbers should be equal to each other once we sum over all the internal color indices. So that's how we see that these occupation numbers map to each other, the total occupation number. So with that, I end my talk here.
We have time for a few questions. So I actually have a question. So you talked about a bosonic exclusion principle because of this Bose-Fermi duality. So similarly, is there some Fermi condensation?
Fermi condensation is there for the fermionic theories. Okay. Yeah, that is usual. As I mentioned that when you turn on the Chern-simons interactions, because in the free fermionic theory, we know that Fermi, they develop a Fermi sea at finite chemical potential. What happens is that at when you turn on the Chern-simons interaction, the Fermi sea behavior is not, modified qualitatively. Yeah.
Thank you.
Hello. Yes. So you mentioned that some of these theories can be holographic.
Yeah.
So is there like a holographic interpretation of this bosonic exclusion thing? Or
it could be, but I did not explore that.
Okay, but does it exist for the holographic theories, or it's only in?
I don't know. Sorry. Yeah.
Okay, thank you.
Yeah. Amiya, I have a question.
Yeah.
Can you briefly explain what is level rank duality? Because
the level rank duality is that, suppose in terms of the Young diagram, if you consider the statement of level rank duality is that you exchange the rows of the Young diagram with the columns of the Young diagram.
okay.
Yeah, and if you consider the gauge groups, for example, SUN at level K, the level rank, rough statement of the level rank duality is that you exchange the labels and the ranks of the gauge. So the level rank dual gauge group of the SUN level K group will be, roughly speaking, the SUK level N.
Okay. Thanks.
If there are no further questions, let's thank Amiya once again.